Okay, you guys, so we're going to get started on 5.2, the definite integral. And in the last class, we basically talked about this value right here. This is our infinite limit of the Riemann sum. And this is basically saying we're going to add up an infinite amount of rectangles or approach an infinite amount of rectangles. And we're going to use that to try to represent the area between the curve and the x-axis. So this will be our representative. Remember, we talked about delta x, we talked about how to find x sub I, and we left off with a problem that was in the right format, but we actually hadn't found the answer. So that's what we're going to continue on with today. So we'll use the definite integral as a symbol to write the area between the curve and the x-axis, because we don't always want to have to write this out. So we're going to develop a new notation to write this. And what we end up with is something called the definite integral. So in this section, we'll deal with the definite integral, and then in 5.4, we'll deal with the indefinite integral. But realistically, they both are working with antiderivatives. One is just a symbol to find the antiderivative, and one is a symbol that uses the antiderivative to help you find the area between curves. So right now, we're going to be working with the symbol, the integrand, or I'm sorry, the integral symbol. So this little s right here is our integral symbol. And again, it kind of looks like S because it stands for the sum, right? Because that's what the Riemann sum is. And then as you see over here to the right, we have the Riemann sum. So we are saying these two things are the same. Now, the other thing is, notice I'm not saying approximately. So when we were first dealing with the Riemann sum and we did like 5, we let n equal 5 and we use 5 rectangles. And you can use other things. You can use parabolas, you can use trapezoids. Those are called the Trapezoid Rule and the Simpson's Rule. Those are other ways that you can generate endpoints and fill in areas, and it just depends on your preference, what you're working with. Also, depending on the shape, one might be better than the other at approximating the area. Those of you that go on to numerical analysis, you might try to do computer programming that you set the computer to do something with this information. But for now, we're just going to kind of focus on left endpoints, right endpoints, and midpoints. So when we dealt with n equals 5 or n equals 10 or n equals 20, we were saying we'd use 20 rectangles or 50 rectangles or 100 rectangles. But as long as we're dealing with an actual number of rectangles, in general, it's going to be an approximation, okay? However, if we can approach a near infinite amount of rectangles, we are no longer going to be approximating, we are going to find the exact area. So that's the big deal. So that's when you start writing this guy right here, limit as n approaches infinity. That's the game changer, because now you are saying you are approaching an infinite amount of rectangles and you're going to try to add that up, okay? So that's what makes it so powerful, and that's what allows us to call it the definite integral. Because if it wasn't the limit as n approaches infinity, it would not be the definite integral. It would just be an approximated sum. But the moment we take the limit as n approaches infinity, we are no longer approximating, we are finding the exact area under the curve. So that's a big deal. Our A and B values right here, those are our limits of integration. You know, sometimes they'll be referred to as a lower bound and the upper bound, or the lower limit of integration, the upper limit of integration, but needless to say, that's what they're called. And let's work on an example. So I may have done this one with some of you in class already. So this is just kind of so you can pause the video and try to keep up instead of kind of, you know, work at the pace I was working at. So I say determine the definite integral from 0 to 3 of x minus 2 squared dx by evaluating the Riemann sum. So we're going to learn the fast way to do this, but right now we're going to use the Riemann sum. And the Riemann sum is the slow, methodical way to do it. And then the definite integral and learning how to work from the fundamental theorem of calculus with the antiderivative is going to be the, I guess you could call it the fast, new and improved way, okay? So let's first learn to do it the slow, methodical way. So we're going to say that the integral, well, I guess we can do it in red. The integral from 0 to 3 of x minus 2 squared dx is equal to the limit as n approaches infinity of the sum of I equals 1 to n, and then it says f of x sub I times delta x. So that means I need to find x sub I, but we know x sub I is always a plus I times delta x. So we need to find delta x, but we know delta x is b minus a over n. So this is going to be 3 over n. because 3 minus 0 is 3. And then we know that this will be 0 plus 3I over n. So we have our x sub I and we have our 3 over n. So we're going to take this 3I over n and we're going to plug it into f. And then we're going to take this 3n and we're going to plug it into there. Okay. So we're going to now have, this equals the limit as n approaches infinity. Oops, that's pretty bad. As n approaches infinity of the summation of I equals 1 to n. And now I'm going to take 3I over n and plug it into my function, x minus 2 squared. So this will become 3I over n minus 2 quantity squared times delta x, but delta x is 3 over n. So this will become the limit as n approaches infinity. And then we just got to do a little bit of our foiling. I equals 1 to n. So I believe this should become, let's see here, 20, oh, not 27 yet. It'll be 9I squared over n squared minus 12I over n plus 4, all times our delta x, which is 3 over n. Okay, so now let's see, we got the limit as n approaches infinity of the summation of I equals 1 to n. And let's distribute that again. So that'll be 27I squared over n cubed minus 12I over n plus, n squared plus, I'm messing up, guys. I was thinking at the same time that I'm writing this. Sorry about that. 36I over n squared plus 12 over n. So that is our sum. All right, so that's not super easy. So maybe pause the video and see if there's any way you can manipulate anything that you remember from pre-calc or whatever knowledge you have of summation, if there's a way you could clean this up, and then the idea of limits. Okay, so you guys unpaused it. So hopefully you're to this point now where you're going to take the 27 over n cubed outside of the summation, and that'll leave me with an I squared minus the limit as n approaches infinity of 36 over n squared times the summation of I equals 1 to n of I plus 12, plus the limit as n approaches infinity of 12 over n times the summation, times the summation of 1. Okay, so I split the limit because the limit of the sum is the same as the sum of the limits, or the difference. And then because our summation has an index of I, everything with the I has to stay inside of the summation, and I mean, technically there's ways you can manipulate it also, but that's in general how we do it. And then anything without the I, we're going to leave behind. Now, the reason we want to do this is because I actually know what the summation of I is worth. I have a few values that I'd like to write down for you guys. So I know that 1 plus 1 plus 1 plus 1 plus 1 equals the summation of I equals 1 to n of 1. Well, this would just be n, because however many ones you add up when you tell me to stop, if you tell me to stop at n equals 8, then I'm going to have 8 total ones, so that'll be 8. So now if we just do 1 plus 2 plus 3 plus all the way up to n, this leads to I equals 1 to n of n, which is just n squared plus n over 2. So these are just summation formulas that different patterns you could have picked up over the years. But if not, let's just do this last one. So this is the sum of all the perfect squares, and this would be the summation from I equals 1 to n of n squared, and that would be 2n cubed plus 3n squared plus n all over 6. So what we're saying is that if you ever get, I'm sorry, I wrote these wrong, you guys, it's with i's. This is I, and this is I. Okay, so what we're saying is if you can ever get a situation like this, a situation like this, or a situation like this, you can replace those with these values. These will be what their sums are. Okay, that's what they sum up to. So I'm going to do that right here. I'm going to say the limit as n approaches infinity, okay, limit as n approaches infinity, I might need to write it a little bit lower. And this will be 27 over n cubed. And then it says that I squared, so I'm going to take directly from here. It says that I squared is worth 2n cubed, the sum of I squared, I'm sorry. And again, these are not imaginary numbers. These are simply summations with an index of I, times 6, minus the limit as n approaches infinity of 36 over n squared. But now we're worried about this guy right here. Oops. We're worried about this summation right here. But that I'm going to replace with this guy. So this will become n squared plus n over 2. I suppose I should have written it in blue. Okay, now let's do the last one. This would be plus 12 over n. Oops, now I'm just messing up. This would just be plus 12 over n times n over 1, which is this guy right here. All right, so now let's see what we got. So this will become the limit as n approaches infinity of 54n cubed plus what, 81n to the squared plus 27n all over 6n cubed minus the limit as n approaches infinity. And again, I'm writing more than you guys probably would want to. I'm just trying to show you guys each step. This would be 18n squared plus 18n all over n squared plus the limit as n approaches infinity of 12, because the n's cancel out. So now I taught you guys in pre-calculus and in the beginning of Calc 1, when you're dealing with rational expressions, the only thing that matters and you're approaching infinity is the dominating term. So we're going to end up with 54 over 6 because the powers are the same. Once again, the powers are the same here, so we're going to be left with 18 over 1 plus 12. So we end up with 9 minus 18 plus 12, which is actually what, 3. So this is the area under the curve. So what we're now going to say is we're going to say the integral from 0 to 3 of x minus 2 quantity squared dx, so this definite integral, is worth 3. And that is our final answer. So you just found the area under the curve of this parabola x minus 2 quantity squared from 0 to 3. Okay? So hopefully that, and again, you guys do not want to do this very often. I think I put like 2 or 3 in the homework at most. This is not something you want to do all the time, but this is the long way to find the area under a curve exactly between the curve and the x-axis. Okay? And these values over here for these summations, you can memorize them, but you can also have them on like your notes or something like that. I often refer back to them. There's one for I cubed as well. Oops, I think I'm leaving one out. This is I squared. Sorry about that, you guys. This is I squared. So you guys, you can feel free to memorize those, but I would just write those on like a little cheat sheet for whenever you need them. They come up sometimes. I'm not going to do a bunch of these. Like I said, maybe one. Okay, so I think that'll be it for that one. Well, I think I'm going to let the homework kind of do this, but basically you can use symmetry and the idea of symmetry. So what if somebody asked you to integrate from -3 to 3 of the square root of 9 minus x squared dx, okay? So I'm going to graph this. I'm going to say, well, we know that they're talking about f of x is equal to the square root of 9 minus x squared. And this is continuous on the interval from -3 to 3, okay? So in reality, what this actually is this is a circle, and it has a radius of 3. You guys know I can't draw, so just go with it. This is good enough. It's supposed to be symmetric here. I'll draw it symmetric. Oops, nope. So that's as good as it's going to get, okay? So this is my x, this is my y. So we have a circle of radius 3, and it's only the positive version, right? Because it's positive in front, it's not negative. So if we graph this on our calculator, you'd get something like this, okay? And they want to know the area under the curve from -3 to 3. Well, wait a minute. Couldn't we just find the area of a circle with radius 3 and then cut it in half? So isn't the area formula just equal to pi r squared? Well, in our case, wouldn't that just be pi times 3 squared? Now, because it's a semicircle, we're going to divide everything by 2. So that means we have 9 pi over 2, and that would be our area, and we'd be done. We didn't need fancy calculus. We needed to recognize what we were getting ourselves into. They want to know the area between the curve and the x-axis. Okay, so we just found it's 9 pi halves. Now, we could, try to integrate or do something like that, but in reality, you guys, you know how to do what they're asking if it's a shape that you're comfortable calculating area for. We already know this formula, so it didn't make it difficult. In your homework, I have a couple where it just asks you to deal with the ideas of graphs. So it won't be necessarily calculation heavy. There will be a few calculation problems, but some of them will want you to just look at the picture and find the area, okay? Let me look at something real quick. Okay, so I just want to kind of talk about a few key points about the definite integral. So, key ideas. Okay, so the first one is, let's just do this. The first idea is the definite integral from a to b of f of x dx is the signed area between the curve and the x-axis. So what this is telling us is that the area above the x-axis is considered positive, and the area below the x-axis is considered negative. Okay, so even though realistically you could never say, oh, I have -5 square feet, when you're talking about this, when you're talking about the definite integral, if you said you had -5 as your area, that means that there is more area below than above the x-axis. Okay, that's all that's saying. Okay. Let me see what else I want to talk about. Something else is the dx in the integral is important. you must write it. Okay. So if you don't write that dx or dy or dg or dz, whatever the case may be, whatever variable you're working with, you're not really doing calculus. It doesn't really make sense to talk about that. So the dx is the change in x's. It's oftentimes referred to as a differential as well. In the Riemann sum, they have delta x for the width of the rectangle. And in our problem, we have the dx serves a similar feature as that. Now the problem is remember, our rectangles are approaching infinite thinness. So as n goes to infinity in the Riemann sum, delta x changes to a dx as a tiny, tiny, tiny rectangle sliver, like just a really tiny slice. And remember, it's approaching infinitely thin, okay? So you must write the dx, and in general, it's assumed to be a very, very small number, okay? But you'll see, especially in 5.5, the dx comes into play even more. You can technically treat dx's and dy's as fractions, as long as they're both recognized as differentials and numbers. But that's a whole nother ballgame. We'll do that in separable differential equations in calculus 2. And the third thing I want you guys to keep in mind is the integral from a to b of f of x dx is a number, okay? And it does not depend on x, okay? So these are some things that we need to keep in mind, that area above the x-axis is considered positive, area below the x-axis is considered negative. F of x dx is an actual number. You're going to find a value, okay? And then, so that means if you turn out to get infinity as the answer, well, that's not really acceptable, because you need an actual tangible area. You can't say, oh, the area is infinite. I mean, you can, but then you're dealing with something that's improper, okay? So the dx in the definite integral is also important, and you must write it. If you don't write it, you're technically learning how to do calculus wrong. It is very important in terms of notation, so please write it. So you should never be writing this, the integral from a to b of f of x. That is actually wrong. You need to write dx, okay? Now, I personally sometimes forget it as well. Everybody does at some point in their life, but I'm trying to teach you guys right, so please learn it correctly, okay? Okay, so I want to give you guys a little bit on properties of definite integrals. So I'm going to give you guys a little bit of a list. This is also in your book as well. So properties of definite integrals. Sorry, you guys, I'm trying to think about the problem that's coming, and it sometimes causes me to write things bad. Okay, so we have some properties. So one of the first properties we're going to learn is that the integral from a to b, the definite integral from a to b of f of x dx, is equivalent to negative integral from b to a of f of x dx. So what this is basically saying is you can manipulate the definite integral limits of integration, but the price you have to pay if you want to flip-flop them is you have to throw a negative in front. Now, if there's already a negative in front and then you flip-flop them, well, then it becomes positive, and vice versa, okay? Second thing is the integral from a to b of c dx is equivalent to saying, so if you integrate some constant, well, that's just going to be whatever that constant is times b minus a, okay? And that actually will become more obvious when we do the fundamental theorem of calculus. Then we have, what if we're integrating from a to a of f of x dx? Now think about this. You're integrating the area under a curve from a to a. Well, then what's the area under that curve? 0. It's nothing, right? Then we also have the integral from a to b of c times the function f of x dx. Now, this is something very similar to the derivative. You are allowed to take the constant out of the integral. You can't mess with the x's or the z's or whatever letter you're working with, or the u's, but you can take the constant out. So this just becomes c times the integral from a to b of f of x dx. Some people like to integrate in u when we learn u substitution or the substitution rule with the constant inside. I'm almost always going to pull a constant out if I'm allowed to, okay? So that's from a to b. The fifth thing we have is the integral from a to b of f of x plus or minus g of x dx is equal. Now, if it were derivatives, are you allowed to split a derivative piece by piece, term by term, when it's addition or subtraction? Yes, you are. So with the definite integral, which is related to the indefinite integral, you're also allowed to do that. So this is going to be the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So you are allowed to split them through addition and subtraction, not through multiplication. Now this is a constant multiple. That is different than a function times another function, okay? Or like an f of x times some g of x. All right, so now step 6 is the integral from a to c of f of x dx plus the integral from c to b of f of x dx is equivalent to saying the integral from a to b of f of x dx. This one's kind of a cool one. What this one's basically saying is, suppose you have some curve that goes like this, right? And here is your A, here is your B, and here is your C. Well, if you find the area under the curve from here, and then you find the area under the curve from here, well, isn't that the same thing as saying the entire area? So if you do the area from A to C of f of x, and you do the area from c to b of f of x dx, let me put the dx here. If you do that, aren't you just really finding the whole area of the whole thing? And that's what this is saying right here. Oops. That's what this is saying right here, is if you break the area into two pieces, but you cover everything, well, then you're still finding the total area from A to B. So that's something else you can do by splitting integrals up. You can still find the whole area. So these are some of the common techniques that we're going to use. And in your homework, there's a few problems like this where it says, given that the integral from -2 to 1 of f of x dx equals 7, and the integral from 1 to 3 of f of x dx equals 5, the integral of 2 to -2 of g of x dx is equal to 3, and the integral from 2 to 3 of g of x dx equals -8. So because of that, they're going to say, okay, we've given you all these things. We actually haven't shown you how to integrate, but we've given you some properties. So could you answer this question? What is the integral from 3 to 1 of f of x dx? Okay. Well, we know that we could factor out a negative. I shouldn't say factor out. We could put a negative in front and go from 1 to 3 of f of x dx. By putting this negative right here in front, I'm allowed to manipulate the limits of integration, okay? But we now know that the integral from 1 to 3 is this guy right here. So this is going to be worth -5. Oops. -5. Now, a second problem will ask, what about the integral from -2 to 3 of g of x dx? Well, we look at g of x, we have from 2 to -2, and we have 2 to 3, but we don't have from -2 to 3. So we're going to have to split this up. We're going to have to think about this as the number line, or I'm sorry, as a graph of some kind. We don't know exactly what it is or whatever. But let's say we're going from, oops, let's go over here, from -2, and then it says from -2 to 3, like this. That's what we want to know. But they told us that 2 to negative 2 of g of x is worth 3. So that means we're going to go and rearrange this from negative 2 to 2 of g of x, right, dx. Now we know from negative 2 to 2 has to be a negative of whatever it used to be because I rearranged the limits of integration. And I'm going to do plus from 2 to 3. So I'm now using this guy and this guy, but I'm rearranging it in a certain order of g of x dx, okay? Now let's see if we know, okay? So from negative 2 to 2 should be negative 3, right? Because from 2 to negative 2 is 3. So if I rearrange the limits of integration, it should be negative 3 plus from 2 to 3 of g of x is negative 8. So we get negative 11, okay? So hopefully you guys understand what I'm doing is I'm using all of these properties, all of this given information, and I'm using the properties up here to rearrange everything. So I use this property like twice, and then on the final problem, I use this property right here that said you can take one integral and split it up as 2, or take 2 integrals and write it as 1, right? So hopefully that makes sense to you guys. And there's a few homework problems like that that should be able to get you through. Let me know if you get stuck on any of this and ask me for help. But overall, this is kind of a general idea how you can manipulate things with the properties that I've listed above. I'm going to end the video now, so I will see you in the next meeting.